medium children, we'll go to the next part of this subunit. In the last class, we were studying about Huygen's principle, and we proved the laws of reflection based on Huygen's principle. As you all know, Huygen's principle, the first one is each point in a given wavefront act as the source of secondary disturbances. Envelope of all the secondary disturbances gives rise to a new wavefront. This we applied and we proved the laws of reflection. Now we are going to prove the laws of refraction based on Huygen's principle. So what is the first law? That is, the incident wave, the refracted wave and the normal all lie in the same plane. That we know. The second one is what is called as Snell's law. What is Snell's law? Mu, the refractive index, is equal to sin I by sin R. So this is what we are going to prove. These two laws of refraction we are going to prove now. Mu equal to sin I by sin R. Now let us consider a refracting surface. Let this be a refracting surface, or this is an interface separating two medium. Let this be the rarer medium and let this be the denser medium. So rarer medium, let V1 be the velocity of light in this medium. Let V2 be the velocity of light in this medium. The refractive index of this medium, let us consider to be mu. Mu is the refractive index of this denser medium. Now, let ABC represent a section of a plane wavefront which is incident on this refracting surface at an angle I. This is a portion of a plane wavefront. I mark it as A, B and C. So ABC represents a section of a plane wavefront which is incident on this refracting surface at an angle I. Now if I drop a normal over here, so whenever you draw a wavefront, the rays are normal. The first point of the wavefront to reach the refracting surface is A, that is at time t equal to 0. After some time, the point B, that is the secondary wavelet from the point B, it reaches this refracting surface. So first the point A of the wavefront reaches the surface. After some time, the point B reaches over here. After some more time, the point C of the wavefront reaches over here. So A, B, C, D, I will mark this as. Okay. So A, B, C represents the 3 points of the wavefront. So they are incident on this refracting surface at an angle I. Now, according to Huygen's principle, all the points lying between A and D act as the source of secondary disturbances or act as the source of secondary wavelets. Now, let us calculate what is the time taken for the point C of the wavefront to reach D. So, what is the time taken? We know that velocity is distance by time. So, we need what is the time taken. So, time will be what? Displacement by velocity. What is the displacement? It is CD. What is the velocity? V1. So, I will take CD to be equal to V1 into T. So, the time taken for the point C of the wavefront to reach D is T, where T is equal to, how much is T? CD by V1. Now let us use the Huygen's principle. All the points lying between A and D act as the source of secondary wavelets. So during the time when C reaches D, the secondary wavelet that has originated from A t seconds earlier would have travelled a certain distance in the second medium. See, in laws of reflection, what did we see? The secondary wavelet that started from here would have travelled in the same medium, that is reflection. Now this is refraction, so the secondary wavelet will travel in the second medium. So during the time when C reaches D, the secondary wavelet that originated from A at time t equal to 0 would have travelled a certain distance in the second medium. Now what should we do? With A as center, I will mark this distance as AE. Now can you find out how much is AE? So where CD is V1 into T, AE will be how much? V2 into T. So the time taken for C to reach D is the same as the time taken for A to reach E. But since it is traveling in a denser medium, its speed will be decreased. Therefore, it travels a shorter distance, which means that CD and AE are not equal. Now what should we do? With A as center, AE as radius, draw a circle. Repeat this for all the points lying between A and D. The envelope of all these circles, when you draw, this is the envelope of all these circles, will give rise to a new refracted wavefront. So this wavefront, we'll mark this, if you mark this as F or something, you can mark this as G or whatever. Okay. So this will be the new refracted wavefront formed at time T. Now we know that this is the angle of incidence I. Similarly, this is the refracted ray, this is the normal, this will be the angle of refraction, and you know this is the wavefront and this is the ray, the angle between them is 90. So this has to be 90 minus I, but since this is perpendicular to this has to be equal to R, angle of refraction. So this angle is angle of refraction. So we have used Huygen's principle and we have constructed a refracted wavefront at time T. Now let us find out what is Snell's law we have to prove. For that, in this triangle, that is in triangle CAD, what is sin I equal to? Sin I equal to CD. This is 90 we know, that is opposite side by hypotenuse. Hypotenuse is AD. So how much is CD? It is V1 into T by AD. Similarly, from this triangle ADE, what is sin R equal to? Sin R. Opposite side is AE. What is the hypotenuse? This is 90, isn't it? So the hypotenuse must be AD. So what is sin I by sin R? That's equal to V1T by AD into AD by what is AE? AE is V2 into T. So it is V2 into T. Similarly, you get sin I by sin R is equal to V1 by V2. But what is V1 by V2? V1 by V2, velocity of light in one medium with respect to the velocity of light in another medium is nothing but the refractive index of the second medium with respect to the first medium. Therefore, what is sin I by sin R? Sin I by sin R is equal to mu to 1, which means we have proved what is Snell's law. So using Huygen's principle, we have proved sin I by sin R is this, and from this figure, the incident wavefront, the refracted wavefront and the normal all lie in the same plane, that is in the plane of this board.